So if we know that fossils are preserved evidence of past life, what are they made out of, right? What is a fossil, right? The word fossil typically implies petrification, and that literally translates to make into stone. So what used to be, or an organic bone, an organic shell, organic skin, becomes petrified, and those molecules, those compounds become replaced with geologic material like stone. So for example, petrified wood is a fossil in which the woody organic parts of a tree have become completely replaced with geologic minerals, such as chalcedony quartz. Right? It's very slow, but the tree itself turns to stone. So that's one way it can happen. And that's often the way people think of, right? The soft organic parts or the bone or the wood physically turns into stone as the organic compounds become replaced with minerals. However, this isn't the only way that fossils can be preserved and what can make up fossils. There's several processes that can act on a shell or a bone of a dead organism to enhance this preservation. And we're going to talk about three of those that are the most common: permineralization, replacement, and carbonization. Permineralization means that the hard part itself is not necessarily replaced, right? So if you think of a seashell, the shell itself is not necessarily replaced. Instead, that petrification, the turning into stone, occurs within the void spaces within the shell, right? So this image is showing a seashell that's become filled with, it looks like calcium carbonate, right? So the white bits of this shell, that's the original shell, right? That's just, right, the same composition as it was when this organism was alive. But the openings in the shell where that organism would have lived, rather than being open void spaces, have become filled in with a new mineral, calcium carbonate. Right? This happens because after that organism dies and the flesh, the meat of the organism decays and goes away, you have these void spaces, and water flows through those void spaces. And water isn't just H2O, it also has a lot of compounds dissolved within it, right? So there might be silica ions or carbonate ions or iron ions. And as those ions in the water become super concentrated, they can precipitate out as a solid. Right? So that's how you can get quartz precipitating out into these open spaces, or calcium carbonate precipitating into the open spaces, or iron precipitating into the open spaces, right? So when open spaces, void spaces, become filled with a new mineral, we call that permineralization. And that does not mean that anything has happened to the original material, right? So the seashell, the original seashell, could still be there. That's permineralization. Now, replacement, this is when the seashell itself is actually changed, right? The original composition of the seashell no longer persists. That's what has been changed. So replacement is when the material that made up the original shell, or whatever the original hard part is we're talking about, those compounds go away and become replaced with a new geologic mineral. This image, the shell has been replaced with the mineral pyrite, which is why it's gold and shiny. I love pyritized fossils. Right? So the solutions dissolve the original material and replace it with a new mineral. So it really does look like a seashell, just made out of a different material, such as pyrite. Right? And this replacement can be remarkably precise. So we can see the details of a shell as we can here. We could see the intricate tree rings in wood, or the delicate bone structures, right? So replacement can perfectly preserve the organism, the hard parts of the organism, by replacing all of those hard parts with a new mineral. So we've talked about permineralization, when the void spaces are filled up with new minerals. We've talked about replacement, where the hard parts themselves are replaced by new minerals. Now we're going to talk about carbonization. This occurs not with hard parts like bones, but more often with really thin, soft tissues, such as a leaf or skin, or maybe even hair. Right? And when these soft tissues are compressed between rock layers, they can actually form thin films of carbon. And these thin films of carbon show up as just thin little layers, like a black silhouette of the organism. So here we're seeing a black silhouette of what appears to be some sort of like a plant or some sort of fern. I've also seen carbonized jellyfish, which are super cool. All right, so these are how the actual bodies themselves can be preserved. As we talked about before, you don't have to have the original body in order to get a fossil. You could create a fossil with an imprint. Okay, so an imprint might be a dinosaur footprint, or it could be the imprint of a seashell or something like that. So often seashells that get buried in the sea floor create what we call a mold, right? It's that imprint that bears the surface imprint of the original shell or the original organism. And when the original organism comes away, that mold is the exact reverse, right? So a ridge on the organism will become a dip or a groove in the mold. So in this image, you're seeing a trilobite where the left rock has the original trilobite. The right rock is the mold or the imprint of that trilobite. So I want you to look at this image and think to yourself, what types of fossils do you see here? Oh, there's a lot of them. What types do you see? I definitely see some molds. I definitely see some imprints. It looks like there might also be some original shell left over. That looks like the original color of the shell. So maybe some imprints and maybe some little bit of replacement or permineralization.